Hi everyone, it's Wednesday, which means it's time for another Chem Help ASAP live stream. So as you can see from the title of this stream, we are going to be naming ionic compounds. So we're not going to be dealing with covalent or molecular compounds in this stream, just all the different combinations of ionic compounds. Now I do recommend that you, if you don't have a periodic table handy, that you go ahead and grab a periodic table, because you're going to find that is going to be very useful as we start naming these compounds, especially in terms of determining charges and knowing where things are and knowing what the names of things are. Okay, so I will make sure that I monitor the chat. So as we're working through problems, if you have questions or you don't understand something, please just let me know in the chat, and I will try my best to answer all your questions. Let's go ahead and get started. So we're going to start with very simple compounds. So the simplest ionic compounds are monoatomic ionic compounds. Now, monoatomic does not mean that there is just one of a certain element, but it means that we're going to deal with the element as an ion. So this is going to be different from polyatomic ions, which we will deal with later. So let's go ahead, before we jump into, you can see we've got 3 compounds on the screen. Let's set up some rules first for naming these monoatomic ionic compounds. Okay. So our first rule is we are going to name the cation with the elemental name. So you will remember that your cation is an ion with a positive charge. In ionic compounds, we always write the cation first. And so we are going to name the cation just with its elemental name. So whatever element it is, that is what we are going to name it with. Okay. Oh, good. We've got someone. Oh, from Louisiana. Yeah, that's awesome. Okay. So once we name our cation, then we're going to go to our anion. Now remember, your anion is your negatively charged ion. It is written after the cation. So for our anion, we are going to take the elemental name and we are going to change the ending to IDE. So we're going to name the anion by changing, that's squeezed, sorry about that. Changing the elemental name to IDE. Now, I know these rules, before you apply them, seem a little bit like, wait, what? So this is why we're going to start with really simple examples, and we're going to apply these rules to these examples, and hopefully these rules will start to make a little bit more sense. Okay, so we're going to start with really our simplest compound, a compound that you can probably already name even if you had no idea about naming ionic compounds, NaCl. This is table salt. This is sodium chloride. Okay, but these examples that you already know how to name are really useful especially if you're in a test and you're a little bit panicky and you're forgetting your rules. These compounds that you already know so well can help you remember the rules. So let's first identify our cation. Our cation is Na. This is sodium. So we're going to name our cation with its elemental name. That is simply sodium. And that is our cation name. That's it. Now we're going to name our anion. Now, our anion is chlorine, but we're not going to name it chlorine, I-N-E. We need to change that ending to I-D-E, so it's sodium chloride, which again, you probably already knew. And that is why NaCl, i.e. table salt, is called sodium chloride. So again, it can be helpful to take that really simple example, and if you need to reverse engineer it, you can. Okay, but let's go on to some other compounds that maybe you don't know just right off the top of your head. So K2O. Again, these are still monoatomic ions. It does not matter that there is a 2 there because the ion itself is just potassium, which is K. So Potassium is the cation. It's okay that there are two potassiums. We're still going to name it with its elemental name, potassium. Okay, that is our cation. Now we need to identify our anion. It's just written after the cation. Our anion is oxygen. Now again, we don't just write oxygen. We need to change the ending to IDE, and this is a little bit weird for oxygen until you get used to it. But to change that ending for oxygen, we call it oxide. And that's it. That is the name of K2O. It's simply potassium oxide. Okay, so hopefully we're getting a little more comfortable with the rules. Let's keep on doing some more examples. All right, cation. Al, this is aluminum. Again, we just name it with its elemental name, no big deal. Now, for our fluorine, you notice we have 3 of them. Again, it does not matter. This is still considered a monoatomic ion because it is the element that is acting as an ion. So fluorine, which is F, becomes fluoride. Which you probably recognize from, going to the dentist, right? So you can even go back and look on your tube of toothpaste now, and you can see that you don't just have fluoride in your toothpaste, but you probably have sodium fluoride in your toothpaste. Okay, we're going to work some more examples, but we're still going to be following these rules right here. But I just wanted to make sure we had plenty of space. So again, lots more elements. Again, this is where it's helpful to have your periodic table handy, especially if your periodic table has the names of the elements, which I do recommend for this. That can be very helpful. Okay, so I'm just going to start in the upper left-hand corner. So I'm going to name my cation again with my elemental name. So Ba is simply barium. That's my cation. My anion is Br. Again, it doesn't matter that there are 2. It's still bromine, but I've got to change the ending to IDE. So that's bromide. And that is the name of BaBr2. Okay, next. Cation is Ca. This is calcium. Because it's the cation, again, it's just the elemental name. We don't change anything. Now, Se is selenium. Again, we change the ending to IDE, selenide. And that's it. Okay, we've got 2 more examples. Again, identify the cation. That's written first. Be is beryllium. And I always have to check how to spell beryllium, because I always forget that it has 2 L's. But again, we named the cation with the elemental name. Yes, there are 3 of them, but that doesn't change our name at all. And now P is phosphorus. But again, we need to change the ending to IDE, so it becomes phosphide. Okay. Last example for our simple monoatomic ions, and then we're going to start bringing some other things in. Okay, so cation, Al, this is simply aluminum. O, again, is oxygen. This is our anion. We need to change the ending and make it IDE, so it is aluminum oxide. So I find that having the molecular formula and getting the name is usually pretty simple. But sometimes we're given the name and we have to work back to the molecular formula, which means we're going to need to do a little bit of math. So let's do that. So here you can see we have some names of compounds, and we need to work backwards and come up with the molecular formula. So the way we're going to do this, let's get some rules up, is we're going to identify our cation. So we need to know what our cation is, and we also need to know what its charge is. So we'll say identify cation and its charge. And we're going to do the same thing with the anion. We need to identify the anion, and we also need to know what its charge is. And its charge. Once we've identified both along with their charges, our final step is to make a neutral compound. This sounds easy, but this is the part that's going to take a little bit of math. So when we make a neutral compound, that means our charges need to add to 0. Now to do that, sometimes we have to use multipliers. And again, this is best seen in practice. So this is why we are going to take these names, and I have more examples too. We're going to identify the cation, the anion, the charges, and then make neutral compounds. All right, so let's start with our cation. Remember, cations are always written first, and they have a positive charge. So this can help just remind you of, this element has a positive charge, or this element has a negative charge because it's written first or it's written second. Okay, so the symbol for calcium is Ca. Now, if you find calcium on your periodic table, you'll see that it is in the second column. That means that when calcium is an ion, it is going to have a charge of +2, although we usually write it as 2+ when we write charges down. That is our cation. We've identified it, and we've identified its charge. Now let's move on to the anion. Our anion is oxide, and you probably remember from all of our previous examples, oxide comes from oxygen. Again, if you find oxygen on your periodic table, you will see that it's in, well, depending on how your periodic table is organized, either column 16 or column 6. So when oxygen is an ion, it has a charge of -2, or again, we write it as 2-. Okay, so we've identified our cation, we've identified our anion, we have our charges, we need to make a neutral compound. So our charges need to add to give us 0. Well, so right now we have a +2 charge and we have a -2 charge. Those already add to give us 0. So we don't need to change this formula at all. It's fine just the way it is. So we simply write CaO because we only need 1 calcium atom to 1 oxygen atom. And while you could write 1s down here, we don't typically do that. I'm going to erase those. We just leave it alone. So we assume it's 1 if nothing is written there. All right, let's keep going. We're going to do some more complex examples where we're going to have to do some multipliers. All right, so sodium sulfide. Our cation is sodium. Its symbol is Na. Again, find sodium on your periodic table. You'll find it's in the first column. When sodium becomes an ion, it has a +1 charge. All right, that's our cation. Now let's do our anion. Sulfide came from sulfur. Again, if you find sulfur, it's right under oxygen. When sulfur is an anion, or when it has a charge, it has a charge of -2 or 2-. Again, we need to make a neutral compound. Let's see where we are right now. So we have a charge of +1 from sodium, and we're adding it to our charge from sulfur, which is -2. So right now we have an overall charge of -1. Clearly, this is not neutral. And we have too much negative charge. We need to bring in some more positive charge, right, to balance this out. Now, when we're trying to make this neutral compound, we can use multipliers. So we're not going to add anything. We're actually going to be multiplying. So I can multiply the sodium by something, or I can multiply the sulfur by something. But to make this add up to be 0, what I think is going to be best is, what if I put a multiplier of 2 in front of my charge for sodium? So now I have 2 times +1 plus -2, which now does give me 0. So I needed that multiplier of 2. I specifically needed it on the sodium, which means when I write this formula, I'm going to put a 2 as a subscript right next to the sodium. Again, when you use these multipliers when you're making neutral compounds, they must always be subscripts. Okay, any questions about that? Okay, so far so good. Let's keep on going. Again, this takes a lot of practice to get used to these things. Magnesium phosphide. Again, same rules. Identify my cation, identify its charge. So we have magnesium, which is just Mg. Again, if you find it on the periodic table, you're going to actually, maybe I'll give you the atomic number. That might be easier. The atomic number is 12. It's in the second column. When magnesium becomes an ion, it's going to have a charge of +2. All right, that's our cation. Let's do our anion. Phosphide, that came from phosphorus. That is P. So if you find phosphorus, it's atomic number 15. It's right under nitrogen. When phosphorus becomes an ion, becomes an anion, it has a charge of -3. Okay, so let's just see where we are. We have +2 from magnesium, and we're going to add it to a -3, and that's going to give us a -1. So we definitely don't have a neutral compound here. So how do we reconcile this? Because I can't just multiply, say, my phosphorus by 2, and that's going to turn it into a neutral compound, but maybe that could help. So 2 times -3 gives me -6. What if I then multiplied my magnesium by 3? So let's double check this. 3 times 2 is 6, plus 2 times -3 is -6. That does give us 0. So this does work. So we're going to have 2 multipliers in this compound. We have a 2 with the magnesium, so we're going to write Mg, again, 3 with the magnesium, with a 3 as a subscript. And then the phosphorus, we use a multiplier of 2. And so that is our molecular compound. Now, let me show you with problems like this, there is a little bit of a trick that you can use. It's called crisscross. Now, be careful with crisscross. It is a fantastic tool, but I will have other examples where I'll show you crisscross does not always work. So just be careful with it. Know when to use it and when to not use it. So let me rewrite this magnesium phosphide just as its ions again. So we have magnesium with its charge of +2 and phosphorus with its charge of -3. And crisscross means is that I'm going to take the number, so I'm going to take not the sign of the charge, but just the number, and I'm going to cross it. So this 2 is going to come down to the phosphorus, and this 3 is going to come down to the magnesium. And you can see I'm getting the same answer that I got before. Mg3P2. But I do want you to understand why it works, and it works because of this algebra right here. So crisscross is great, and you can use it in a lot of different situations, but again, I'm going to show you situations where it is not going to work, so just be careful. Okay, doesn't look like there are any questions, so let's do some more examples. And you can see we've got 4 here. So we have, let's switch back to blue. Beryllium chloride. All right, so beryllium, here's our cation. Symbol is Be. It is in your second column. So when beryllium has a charge, what charge does it have? It has a charge of 2+. Okay. Chloride came from chlorine. Chlorine's one of the halogens. Its symbol is Cl, and of course when chlorine becomes an anion and has a charge, it has a charge of -1. Okay, so let's check and see if we have a neutral compound. We've got beryllium, which is +2, plus our chlorine, which is -1, and that gives us an overall charge of +1. So looking at that, I think, all right, I need to bring in more negative charge. How much more negative charge? Again, I've got to make this 0. So I need some kind of multiplier, and that multiplier is a 2, because now I have 2 plus a -2. That will give me 0. That gives me a neutral compound. So my final formula is BeCl2. Again, this 2 came from the chlorine. Let me show you how this works with crisscross, because you can use crisscross on this one. Again, we're just taking the number. You don't take the charge. So this 2 comes down here to the chlorine, and this 1 comes down to the beryllium. And again, we don't write the 1 down, and you can see I get the same formula. Okay, let's go to our next example. Potassium iodide. Identifying our cation first, potassium. So if you're finding potassium on your periodic table, you're going to find it in the first column there. So when it becomes an ion, it has a charge of +1. Iodide is another one of the halogens. So when it becomes an ion, it has a charge of -1. Okay, so let's check our charges. You can already see that +1 plus -1 gives me 0. And so this compound is already made. We don't have to do anything. It can be easy, especially when you get going with these more difficult problems, to just keep trying to make this really difficult, but always check and make sure if you already have a neutral compound with having one of your cations and one of your anions, and then you just don't have to do all that extra work. Okay, we're almost there with these examples. Aluminum sulfide. So aluminum is Al. If you find it on your periodic table, it's actually more on the right-hand side. It has a charge of 3+ when it becomes an ion. And sulfide comes from sulfur. Again, you can find sulfur right under oxygen. When sulfur becomes an anion, it has a charge of -2. Okay, so now what we want to do is let's go ahead and work through our algebra, but you can also use crisscross on this. So our algebra right now, we have a +3 plus a -2. This is definitely not giving us 0, but again, there's not a really simple multiplier here. You're like, oh yes, just multiply this one by 2 or multiply this one by 3. What we're going to have to do to make this work algebraically is, of course, we're going to multiply our cation by 2 and our anion by 3, because then we have a +6 plus a -6, which does give us 0. So this gives us a neutral compound. That's no longer 1, but that is 0. Again, the crisscross works for this example just fine. So this is going to be Al2S3, and I'll show you where the crisscross comes in. This 3 comes down to the sulfur, and this 2 comes down to the aluminum. Again, it's really important that you don't bring these signs down. And you'll never see, like if you look through your chemistry book, you'll never see a subscript with a -2 in a molecular formula. Like it's always positive. We can't have negative atoms in a molecular formula. Okay, let's just make sure there are no questions. And let's do our last example again for our monoatomic ions. Okay, our cation is lithium. That is Li. If you find lithium on the periodic table, it's in that very first column. So when it becomes an ion, it has a charge of +1. There's selenide again. So if you find selenium, it's under sulfur, which is under oxygen. So when selenium becomes an anion, it has a charge of -2 right here. So let's see where we are with our charges. We have a +1 from the lithium plus a -2 from the selenium, and this is going to give us -1, so we need more positive charge. So in this case, we want to multiply our cation by 2, and then that will give us a neutral compound. Again, you can use crisscross. This 2 comes down to the lithium. This 1 comes down to the selenium, but of course we don't write it down because we don't write our 1s down. So you can see I'm getting the same thing using both methods. So again, crisscross is great, but if it doesn't make sense to you and you like the algebra better, go with the algebra. If you don't really like the algebra, go with the crisscross, but just be a little bit careful with it. Again, we're going to see examples where crisscross is going to mess you up. So these are all our monoatomic ions. And so next I want to start introducing our polyatomic ions. Let's make sure there are no questions before I go on. Okay, let's keep going. So what I've done here is I've given a list of common polyatomic ions over here on the right-hand side. These may or may not match up with all of the polyatomic ions that you need for class. Sometimes they do, sometimes they don't. I find these, again, are the most common. You might have more that you have to deal with. You might have fewer that you have to deal with. But for all of these problems that have polyatomic ions in them, I'm going to keep the list of polyatomic ions here on the far right-hand side so that we can reference it. Now, for your classes, probably most of you are going to have to memorize some set list of polyatomic ions. And that is important because when you're trying to name things quickly, you want to be able to just remember them. Oh, yes, NO3 is nitrate. It has a charge of -1. It's kind of a bear to memorize. I hate memorizing, but this is one thing that actually does need to be memorized. But for our live stream here, we're not going to have to memorize it. We're going to have our list right here. And of course, our periodic table. So let's talk about naming compounds with polyatomic ions. All right, so let's set up some rules just like we did before. All right, so we're going to name our cation with either the elemental name, just like we've done before, or, whoops, let me put space. I combined name and or with its elemental name or the polyatomic name. And I'll give you a little bit of a spoiler here. We only have one polyatomic cation, and it is ammonium right here. So if your cation happens to be ammonium, then we just call it ammonium. Like it's not that secretive or complex. Okay, so that is our cation. For our anion, we're going to name using the polyatomic ion name. Now, all of these examples have polyatomic ions because we are working with polyatomic ions, but you need to be ready, and we'll do this in later examples, where you need to be able to identify, oh, this is a polyatomic ion, I need to use that name, or oh, this is a monatomic anion, and I need to change the ending to IDE. But for now, we're just going to focus on the polyatomic ions. Again, we're starting with the molecular formulas, and we're going to the name because I think that is easier. So, KClO3. The fact that you've got 3 elements here should raise some red flags like, whoa, we've got something else going on than just monoatomic ions. And this, again, is where it's really helpful to have your polyatomic ions memorized because it makes it really easy to identify, oh, I think I have a polyatomic ion here. But let's start with our cation. And of course, our cation is simply K, which is potassium. And again, we're just going to predict like we did just previously. When potassium becomes an ion, it has a charge of +1. Great. ClO3. This is clearly not a monoatomic ion because we have 2 elements. So you remember your monoatomic ions, even though you might have 2 or 3 of them, it was all the same element. That's what we mean by monoatomic. It's all the same element. These are polyatomic. It's going to be more than one element. In this case, we've got chlorine and oxygen. So what we need to do is we need to go over to our list of polyatomic ions and find ClO3. ClO3 is right here. It is chlorate. Oh, and see, I just wrote potassium here. I need to write potassium, write it out as the word. I'm already ready to take the name and do our math with it. Okay, so that is potassium. Again, this was chlorate. And that's it. This is potassium chlorate. Bam, you're done. Okay, let's go on to our next one. Again, we've got 3 different elements, so what is going on here? Well, I have slipped in our one and only polyatomic cation, and that is NH4, and you can see NH4 is right here. This is ammonium. So we just call it ammonium. We don't change the name, we just call it ammonium. We use the name that's already given to us. And that's our cation. Bam, we're done. Okay. But our anion here, because we don't have to do this. The cation was a polyatomic ion, but if you look at our anion, it is back to a monoatomic ion. This is just Cl. It's just chlorine as an ion, which means this ending needs to be IDE. So you always need to be ready to be a little bit flexible and go, oh, this is a monoatomic anion. I need to change the ending to IDE. Or this is a polyatomic ion. I just need to name the ion. Let's make sure there are no questions. Okay, great. Let's keep on rolling. Again, identifying our cation as Na, which is sodium. Even though there are two, it doesn't matter. We just call it sodium. All right, that's our cation taken care of. Now our anion, again, polyatomic, we've got sulfur and oxygen. We've got SO4, so we need to find that on our list. So if we look on our list, you can see SO4 down here is sulfate. So I just use the name of the polyatomic ion, sodium sulfate. I kind of think it's nice to have the polyatomic ions because I don't have to worry about changing the ending to IDE. I just use the name of the polyatomic ion. Okay, let's keep on going because we have more examples. Al here, this is our cation. It's aluminum. We just use the elemental name. Okay, that's great. Our cation is taken care of. Now we have this NO3 with parentheses and a 3 out here and a 3 here. And what's going on with this? All we have to do is identify the polyatomic ion. And the polyatomic ion is within the parentheses, NO3. Let's go to our list and find it. And you can see here it is right here. This is nitrate. That's it. So I think a lot of times students try to take the molecular formulas to the names and try to make it more complex. This should be really, really easy. You're just naming the cation and you're naming the anion, and that's it. You don't have to tell me how many of each we have, because if I know my chemistry and I know my naming, then I already know the charges on them. Okay, let's do our next example here. Mg, this is magnesium. And that's it for our cation. Our anion is Cn, which is a polyatomic ion. Yes, there are two of them, but we don't need to worry about that. We just need to find Cn on our list. And here it is right here, cyanide. And bam, you're done. That's it. Okay, make sure there are no questions. All right, great. We're going to still go on with some more here. Okay. So again, we're just using the same rules. We're going to identify our cation. We're going to use either the elemental name or the polyatomic name in the case of ammonium. And then we're going to identify our anion. And most of these, again, are going to be, actually all of these are going to be polyatomic ions. We just use the name of the polyatomic ion. So again, hopefully as we do these examples, you're seeing, oh, this is really easy. I hope that's what you're saying. So Ba, again, you just find it on the periodic table. This is barium. Okay, you're done with your cation. That's all you need to do. Our anion, again, is a polyatomic ion. We have chromium and oxygen, so we just need to find it on our list. So if we're looking, we can see here it is. This is chromate. And that's it. We're done. That compound is named. Let's keep on rolling here. Li is lithium. Again, yes, there are 3 lithium atoms, but that doesn't matter. It's still just lithium. So we just name it lithium. And now for our anion, it is a polyatomic. It's PO4. So we need to find PO4 on our list, which is down here. This is phosphate. And that's it. You're done. Okay, on to our next one. Ca is our cation. That's calcium. Now notice here for our anion, again, we have the parentheses and we've got a 2 on the outside. That just means you have 2 of these anions, these polyatomic anions. The anion itself is within the parentheses, NO2. So that's what we want to look for. So when we're looking on our list, we can see NO2 right here. This is nitrite. And this is where you do want to be careful as you're memorizing. You'll notice we've got nitrite, which is NO2, and nitrate, which is NO3. Those are easy to mix up. So just make sure you've got them straight in your head, which is which. All right, we're almost done with these. We've got NH4, and we've been given parentheses to really highlight that that is our cation, but it is a polyatomic cation. It's our only polyatomic cation, and that is ammonium. Okay, so that's it for our cation. Our anion is OH. Again, we have an oxygen and hydrogen. It's polyatomic. So as we're looking down our list, here we find OH. That is hydroxide. And bam, that compound's name. We're done. Okay, last one. We got our cation. This is potassium. Again, yes, there are two of them, but it doesn't make a difference. We just still call it potassium. Okay, great. Our cation is named. Now for our anion is Cr2O7. So we just need to find this in our list. So you can see this is dichromate. And don't let the di here fool you or throw you for a loop. That is the name of this polyatomic ion. It happens to refer to how many chromium atoms you have, but that is the name for the polyatomic ion. You just name the polyatomic ion. So this di does not mean that there have to be two of these or anything like that. That is simply the name of the polyatomic ion. Okay, so hopefully these were easy for you. I don't see any questions, so I'm hoping that you found them very easy. And now what we want to do is we want to do the reverse. This is going to be a little more difficult because we're going to have to use our math, just like we did with the monoatomic ions, because we need to make neutral compounds. So just like we did before, let's just set up a couple of simple rules. So yeah, just like with the monoatomic ions, we want to identify our cation and identify the charge on it. So identify our cation and charge. Same thing with the anion. We want to identify it and know its charge. And then the last step, which is the most difficult, is make a neutral compound. All right, so best way to do this is just to practice. Lithium hydroxide. Lithium is my cation. Again, if you ever forget, like, oh, is that going to be a positive charge or a negative charge? It's written first. It's the cation. It's going to have a positive charge. So the symbol for lithium is Li. Again, if you find lithium on the periodic table, you'll find it in that very first column. So when it becomes an ion, it has a charge of +1. Okay, that's our cation, at least identified with charge. Now let's do our anion, hydroxide. Now this one can be a little tricky, again, if you don't have your polyatomic ions memorized, because you're seeing this ID ending, and so you're trying to find some kind of like hydroxygen or something on the periodic table, but this is actually a polyatomic ion. So here it is right here, hydroxide. So if you're ever really struggling to find an element on the periodic table, then it might be a polyatomic ion. So hydroxide is OH, and it has a charge of -1. Okay, so we've got our cation, we've got our anion, we've got our charges on both, so we need to make a neutral compound, just like we did with the monoatomics. So we need to do a little math. So our lithium has a charge of +1, plus our hydroxide, which has a charge of -1. And you can see that already gives us an overall charge of 0. This is a neutral compound just as it is. So all I need to do is write LiOH, and that's it. You don't need parentheses. You don't need to write ones anywhere. That is lithium hydroxide just like that. Okay, let's go on to our next one. Our cation, calcium, is Ca. Again, you need to find this on the periodic table. It is an element. You'll find it in the second column. It's atomic number 20. When it becomes a cation, specifically, it's going to have a charge of 2+. Okay, so that's our cation. Now let's do our anion. Carbonate. Usually this ate, those tend to be polyatomic ions. So hopefully, like, again, you're getting your red flags waving saying, hey, check your polyatomic ion list. This doesn't look like a monoatomic ion. So let's find carbonate. And you can see it's up here, right there. So I am just going to write this down. This is CO3 with a charge of -2. Again, when you're memorizing your polyatomic ions, you do want to make sure that you memorize the charge as well as the molecular formula, because you can see that knowing the charge is really important for putting together a neutral compound. Okay, so calcium carbonate, let's check our charges because we need to make a neutral compound. So calcium gives us a +2, carbonate gives us a -2, so we're set. We've already got 0. This is an example of where crisscross is going to mess you up. So if you didn't check to see if you have a neutral compound first, what are you going to do? You're going to take this 2 down here and this 2 over here, right? But you don't need to do that because you already have a neutral compound. So you do not want to crisscross here because your compound should just be CaCO3. But if you accidentally crisscrossed, you would end up with Ca2CO3, and that is not right. So again, know the limitations of crisscross. My best advice is make sure that you don't already have a neutral compound, because those are usually the cases where crisscross is going to mess you up. Okay, so calcium carbonate is just CaCO3. Bam, plain and simple. Let's go on to our next example. Magnesium, identify our cation first. That is Mg. Again, if you find it on the periodic table, atomic number 12. Yes, atomic number 12. When it becomes a cation and it has a charge of 2+. Okay, so that's our cation. Now let's identify our anion, nitrate. Again, this ATE ending can help send you to your polyatomic list and not the periodic table. So let's find nitrate. Here's nitrate right here. So I'm just going to write this down as is, NO3, and it's got a charge of -1. So let me check and see if I have a neutral compound, even though, yes, I know it doesn't already have it's not going to be neutral. So that is equal to +1 right now. I got to make sure I leave space for aluminum sulfate. Okay, so this is not a neutral compound. So we've got two choices. We can use crisscross or we can use a little bit of algebra. I'll show both ways. So for this one, if I put a 2 in front of my -1 charge, then that is going to get me to a neutral compound. And of course, my crisscross, I'm going to take this 2 over here to the nitrate, and the 1 goes to the magnesium. And let me show you a common mistake that students make. So we've got Mg, we've got our nitrate, and then students are not sure what to do with that 2. Sometimes that 3 somehow gets erased and the 2 goes there instead, but that's not nitrate anymore, that's nitrite, so that is not correct. Sometimes what I see is the NO3 stays intact and the 2 goes next to it, but then what that actually says is you have 32 oxygens, and that is not correct. What we want to do is we want to specify that we don't have a lot more oxygens. We need 2 of our nitrate polyatomic ions. And the way we do that is with parentheses. So you saw that when we took the molecular formula to the name, and maybe you kind of noticed it, maybe not so much. But those parentheses are key to say how many of those polyatomic ions, you can think of them as units, how many of those units do you need? And in this case, we needed 2. Okay, does that make sense? All right, I hope so, because that is a very common mistake that students make. Okay, let's go on to our next one, potassium phosphate. Potassium, let's do our cation first. Potassium is K. When it has a charge, it's +1. Phosphate, again, hopefully the ATE ending clues you in that we need to go look at the periodic table, not the periodic table, at the polyatomic ion list. Here we go. Phosphate is down here. So this is PO4 with a charge of -3. So let's check if we have a neutral compound. No, we don't have a neutral compound, but let's write it down. This right now gives us an overall charge of -2. So we've got way too much negative charge. We need some more positive charge here. So in this case, what I need to do is I need to multiply here by 3. And then that gives me an overall charge of 0. Now I've made a neutral compound. Again, if you're doing crisscross, this 1 comes down to the phosphate. This 3 comes down to the potassium. You can see we're getting the exact same answer here. So this is going to be K3PO4. SO4. And again, this one that came down from the potassium, where you can think of the one that we didn't have to put a multiplier here, you don't have to use parentheses and a 1 on the outside. You just simply write PO4. Let's do our last one on this page. I know these are tough. We're going to practice some more. Okay, so we have aluminum sulfite. Aluminum is our cation. Al, again, if you find it on the periodic table, you can predict that it's got a charge of 3 plus. And sulfite, so if we're looking for sulfite, here it is right here. Again, hopefully this ITE ending kind of clues you in. Check your polyatomic ion list. So sulfite is SO3 with a charge of -2. Let's check and see if we have a neutral compound. Spoiler, we don't have a neutral compound, but let's write it down. Plus a -2. Of course, that gives us an overall charge of +1. So again, we can do crisscross or we can do our algebra, either way. So we're going to need to put a 2 in front of our aluminum and a 3 in front of our sulfite to make this neutral, so that now equals 0. Or again, our crisscross, you take your 3 down here and you take your 2 down to your aluminum. So this is going to be Al2. Again, don't forget your parentheses. SO3, 3. Make sense? Okay, let's keep practicing. Because again, these are difficult, especially getting the crisscross, and it's really hard sometimes not to take that negative down, but don't take that negative down. Okay, so we've got 5 more examples here. Boron perchlorate. Let's find boron. So boron is atomic number. What is atomic number? Atomic number 5. When it has a charge of +3. Okay, that's our cation. Our anion is perchlorate. Again, ATE. Let's go check our polyatomic ion list. It's right there. So that's ClO4 with a charge of -1. Do we have a neutral compound? No, we don't have a neutral compound, but we'll write it down anyway. Plus a -1. This is going to give us a +2. So obviously we need a little bit more negative charge. We need some more anions. So if we put a 3 in front of here, now we've got a neutral compound. Again, crisscross. Your 3 comes down to your perchlorate and your 1 goes down to your boron. And we get BClO4. And again, use those parentheses anytime you need a multiplier on your polyatomic ions. On to the next one. Beryllium phosphate. So beryllium, when we find beryllium, that is Be. When it's an ion, it has a charge of 2 plus. Phosphate, again, 8. Let's find our phosphate down here. Here it is right here. This is PO4 with a charge of -3. So let's check our algebra. Beryllium's charge plus phosphate's charge. Nah, this ain't going to work, is it? And there's not a simple multiplier that we can either do on the cation or the anion. We're going to have to do both. So here's our algebra. We need 3 berylliums and we need 2 phosphates, and then that is going to give us our neutral compound. And crisscross looks like this. 2 comes down here. 3 comes down here. So let's write beryllium phosphate. So that is Be3. PO4, 2. Okay, beryllium phosphate. Ammonium dichromate. So ammonium, remember that's not an element. That is our polyatomic ion. That is our cation. Okay, so you're not going to find ammonium on the periodic table. We just need to write down what our polyatomic ion is and its charge. So that's NH4 with a charge of +1. Dichromate, that is another polyatomic ion. So in this case, we've got a polyatomic ion for the cation and a polyatomic ion for the anion. So dichromate, nope, that's chromate. Here's dichromate is Cr2O7, and that has a charge of -2. So again, let's add our charges together, see if we've got a neutral compound. And no, we don't. So that gives us a charge of -1. We need a multiplier. And we need a 2 right here. Again, if you want to use crisscross, The 1 comes down to the dichromate, and the 2 comes down to the ammonia. Now, just like we've been doing for the polyatomic ions that are anions, we need to use parentheses to say that we need 2 of these ammonium cations. So this, whoops, I didn't mean to go yellow. I meant to go blue. This becomes NH4, parentheses 2, that is a 4, and then Cr2O7. Again, because it's a 1, we don't need parentheses with a 1 on the outside. So that is ammonium dichromate. All right, 2 more to go, and then we need to talk about transition metals, which are a little bit more difficult. Okay, barium permanganate. So barium is Ba. When it has a charge of 2 plus. Permanganate is a polyatomic ion, so let's find it. Here it is right here. So that is MnO4 with a -1 charge. So let's just see where we are with our charges. +2 and a -1. Yeah, we don't have a neutral compound, but this is an easy one. We just need 1 multiplier. We just need a 2 in front of our permanganate, and now we've got a neutral compound. Again, crisscross. Bam. Bam. And here is our final compound, Ba. Don't forget your parentheses. MnO4, 2. Okay, last one here. Barium. Oh, no, this is the same one. Sorry, I just wrote it down twice. We've already done barium permanganate. We don't need to do it again. Okay, so hopefully this makes sense. When you're doing your polyatomic ions and you need a multiplier, don't forget those parentheses. Let's make sure there are no questions. Okay, no questions. Let's keep on trucking. All right, so here are the compounds that tend to give students the most trouble when they're naming or getting the molecular formula for compounds, and these are the transition metals. Now, the transition metals can have multiple oxidation states. So you can see in our first 2 examples, I've written iron 2 sulfite and iron 3 sulfite. So what we have to do when a metal can have different oxidation states, and that means it can have different charges. So these are going to be your cations because they're metals. They're going to have a positive charge. When we're going from the name to the molecular formula, which I think is easier with these, the name tells you the charge on the metal. It tells you the charge on the cation because you cannot just simply predict it. So we know when sodium becomes a cation, it's always going to have a charge of +1 unless something really, really weird and unusual is going on. But when we're talking about iron can either be +2 or +3 commonly. It actually can be other things too, but commonly is either +2 or +3. So we need to know which one of these it is. So that's why I think it's easier with these to start with the name because the name tells you what the charge is. Just like before, we need to, I'll write this down, we need to identify the cation and its charge. So identify the cation and charge, and then we're going to identify the anion and its charge, and then we need to make a neutral compound. Okay, so for these next set of examples, you need to be prepared to use polyatomic ions or recognize monoatomic ions. So I mix it up in here so we don't get stuck like always using polyatomics or always using monoatomics. We've got to, again, be able to be flexible and recognize which is which. So let's start with our first example here. So this is iron 2 sulfite. So iron, let's find that on the periodic table. We need to get the symbol for it. Its atomic number is 26, and its symbol is Fe. This 2 here tells us the charge on the iron. The common misconception is students think that that 2 tells you how many iron atoms. It does not tell you how many iron atoms. It tells you the charge on it. So I'm going to write Fe2 plus like this. We need to figure out how many iron atoms we need. Sulfite is a polyatomic ion, so let's find it over here. There's sulfite. So that is SO3 with a charge of -2. So now we proceed just like we've done before when we have the name and we're trying to get to the neutral compound. We're just going to check our charges. So we have a +2 with our iron 2. Our sulfite has a -2 charge. We already have a neutral compound. So all we need to do is write FeSO3. This is another example where crisscross is going to trip you up if you didn't check your charges first, if you didn't check to make sure you had a neutral compound, because if you just jumped straight to crisscross, you would have taken this 2 and taken it down to the sulfite and that 2 down to the iron. But that is not the correct molecular formula. The correct molecular formula is just FeSO3. So again, check and make sure you don't already have a neutral compound. Let's go on to our next example. And you can see it's very similar, but it's not quite the same, but it makes a big difference. So this is still iron, which is Fe, but now it's iron 3, which means the charge or the oxidation state has changed. So this is Fe3+. Sulfite is still the same as up there. It's SO3. It's got a charge of -2. But you can see this is going to change up our math. It's going to change up how many atoms we have of each. So iron 3, of course, has a charge of +3. Our sulfite is still -2. We no longer have a neutral compound, right? We have an overall charge of +1. This is one where crisscross is going to help us. So the 3 is going to come down to the sulfite. The 2 is going to come down to the iron. Again, if you're looking at the math, we need a multiplier of 2 here and a multiplier of 3 there, and that gives us an overall charge of 0. And so iron 3 sulfite looks like this. SO3, 3. So you can see in the name it says 3, but how many iron atoms did we actually need? We only needed 2. So again, that's just a really, really big thing. It's just such a common mistake that I see over and over. Your Roman numeral gives the charge. It does not tell you how many iron atoms you have. Let's keep practicing these. Okay, so we have lead for chromate. Let's get lead first. So lead is all the way like in the bottom right of the periodic table. Let me get the atomic number. Atomic number 82. Its symbol is Pb. This 4, again, tells me the charge I have on the lead. So that has a charge of 4, +4. Chromate, that's a polyatomic ion. Let's find chromate. Here it is right here. So I'm just going to write that down. CrO4 with a charge of -2. Okay, let's see. Do we have a neutral compound? So we have +4 plus a -2. This gives us a charge. That is a 4. That does not look very clear. Of +2. So no, we're definitely going to need multipliers here, but this is a pretty simple multiplier, right? If I put a 2 in front of here, now I've got 0. Bam, I've got a neutral compound. This is another case where crisscross does not actually help you out, because what would happen if you crisscrossed? You would take this 4 down, and then you would take the 2, and that would not be correct, right? Because we actually just need 2 of the chromate. So again, be careful with that crisscross. Now, some people in this case would say, all right, so I'm just always going to use crisscross, but then if I can reduce that ratio, I'm going to reduce that ratio. And that generally works pretty well, but you do have to remember to reduce that ratio. This is why I still like to write the algebra down, because it helps me make sure that I'm using crisscross in the right way in the examples that it works. Okay, so this is PbCrO4, 2, because all we needed was that multiplier 2. Crisscross is no good here. I'm going to write no right there for the crisscross. Don't use crisscross. Okay, next example. Chromium 3 fluoride. So chromium, when we find chromium, its atomic number 24. Its symbol is Cr. Again, the 3 tells me its charge. So that's its charge. Fluoride, oh, we've got an IDE ending. So this came from fluorine. This is a monoatomic ion. So you want to find it on the periodic table. It's a halogen. So fluoride has a charge of -1. Okay, so let's do our algebra. We have +3 plus -1. Yeah, no, this is not going to give us 0. But again, this is pretty easy to find the multiplier that works because all I need is a 3 here. Or crisscross. I always want to say crisscross applesauce. I'm just used to my kids saying that. Okay, so this is going to be CrF3 for chromium 3 fluoride. Again, the 3 did not tell you how many chromium atoms. It just told you the charge. All right, cobalt 2 phosphate. So cobalt, when we find cobalt on the periodic table, which I am looking right here, and I'm having a hard time finding cobalt. There it is, atomic number 27. I wrote calcium. CO, again, the 2 tells me the charge. Phosphate, again, ATE, polyatomic ion. Let's find it. Here's phosphate. PO4 with a charge of -3. Checking our math. +2 plus -3. This is not a neutral compound. This is definitely a case where crisscross is going to be a huge help because I need 2 multipliers here. And now I have an overall charge of 0. And again, the crisscross goes like this. So this is CO3, PO4. Again, because it's a polyatomic ion, make sure you use those parentheses. CO4, 2. That's a 2 right there. Okay, questions? Nope, no questions. Let's keep going. We're almost there. We're getting there. Hopefully this practice is making it easier and making you understand where these things are coming from. Again, these transition metals can be very difficult the first time you deal with it. Okay. Tungsten 6. So you can see these transition metals can have actually really high oxidation states or really high charges. So tungsten is down at the bottom, atomic number 74. Its symbol is actually W. And this 6 tells me it has a charge of +6. Dichromate, let's find it. Here it is right here. Cr2O7 with a charge of -2. Let's do our algebra. We have +6 plus our -2. Yeah, this is definitely not neutral, but what can we do to make it neutral? Okay, so this is, again, another time where crisscross is going to mess you up because we really just need multipliers here. So if I go 3 right here, that gives me a neutral compound, right? Again, if you crisscrossed and you brought the 6 down and the 2 down, you would end up with the wrong molecular formula. So this is actually W for tungsten, Cr2O7, 3. So again, I just want to show lots of examples of be careful with crisscross. It is a great tool, but it does not always work. It only works in the right circumstances. Okay, ruthenium 4 phosphide. So let's get ruthenium. Ruthenium is atomic number 44. Its symbol is Ru. Its charge they gave us is 4+. Phosphide, ooh, IDE. This means it's a monoatomic ion. It's not a polyatomic ion. So a lot of times when you start to memorize your polyatomic ions, when you see phosphide, you immediately think phosphate over here, but those are not the same things. Phosphide came just straight from phosphorus right here. And of course, when phosphorus is an anion, it has a charge of -3. All right, so let's do our math. We have +4 plus a -3. Yeah, this isn't going to work, and we don't have a really simple multiplier here. This is where we definitely need crisscross. So we're going to need a 3 here and a 4 here. That gives me 12 plus a -12. That is a neutral compound. Again, crisscross here is going to help us out. So Ru3P4. All right. Scandium 3 cyanide. So scandium is atomic number 21. Its symbol is S3. That 3 tells me its charge. Cyanide, again, IDE can be confusing in this one, but cyanide is a polyatomic ion. Here it is right here. Cn. This is why it is helpful to have them memorized, because then you can recognize them a little bit easier, a little bit faster. Let's do our algebra. +3 plus a -1. Yeah, this is not a neutral compound, but we can make it neutral. All we need to do is multiply by 3, and now we've got a neutral compound. Or again, crisscross, and that 1 would come down there. So the formula for this is SCCN3. Don't forget in this one, and it is easy to do this with cyanide and hydroxide. Those are still polyatomic ions. You still need to use the parentheses, because if you drop the parentheses in this one and you just write CN3, that means you have 3 nitrogen atoms, but you need 3 cyanide polyatomic ions. Okay, almost done with this page. Osmium 4 sulfide. So osmium OS for, I meant to give you the atomic number 76. So you can see these transition metals tend to be right in the center of the periodic table. Osmium 4, so that means it has a +4 charge. Sulfide, IDE, sulfide. This came from sulfur. So when sulfur becomes an ion, it has a charge of -2. Let's check our algebra. And you can already see we don't have a neutral compound. However, we just need one simple multiplier, right? We just need a 2 right here. And now we've got a neutral compound. Again, crisscross is not working in this case. So all we need is OS, S2. I know that looks kind of weird. So when you write that, make sure that the S for the osmium is smaller than the S for the sulfur. So it makes it really clear that you're talking about osmium sulfide. Okay, last one on this page, manganese 7 oxide. Okay, so manganese is atomic number, what was that, 25. 7 tells me it's charge. Oxide, again, this is a monoatomic ion. It's oxygen, has a charge of -2. Checking our algebra, 2, this gives us a charge of +5. So yeah, this is not going to work. We don't have a simple multiplier here. We are going to have to use crisscross. Oops, let me write that down. So this 7 is going to come down to the oxygen. This 2 is going to come down to the manganese. So we have Mn2O7. Manganese oxide. Let's make sure there are no questions. I don't see any questions. Okay. Okay, so now we're going to go the other way. So we have been given the molecular formula and we need to write the name. The tough part about this is we need to now give the reader the Roman numerals. We need to tell the reader the charge on the ion, or the charge on the cation, the transition metal in this case. And this, I think, when you're dealing with transition metals, it's more difficult to go this way because we still need to do our math. Okay, but let's write down our rules. So we're going to name the cation with the elemental name. Then we are going to specify the charge with Roman numerals. So specify the cation charge using Roman numerals. And then we are going to just name the anion. Again, here we need to be careful. We need to be ready to name the anion as a monoatomic ion, which means we change the ending to IDE. Or if it's a polyatomic ion, we're just going to name the polyatomic ion. So again, this is where we need to be flexible and be aware of all of our sets of rules and use the one that's appropriate in the case that we're talking about. Okay, so let's start with our first example, FeCl3. Well, Fe is iron. That's great. But if you find iron on the periodic table, you can see it's atomic number 26. It's right smack in the middle of all those transition metals. So that should be your sign, hey, you need to specify the charge on that iron. So how do we figure out what the charge on the ion actually is? Well, you can either do crisscross and reverse or you can do your algebra. So iron, we don't know what it is. I'm going to call it X. It's going to have a charge. I don't know what it is. But I'm adding to it 3 chlorine anions. Now remember, chlorine has a charge of -1 when it becomes an ion. And I've already been given the molecular formula, which means this is a neutral compound. So I know this equals 0. All I have to do is solve for X. So it's just a really simple algebra problem. X equals 3. So the charge on my iron in this case is 3. You can also think about this as a reverse crisscross. So I've already circled the 3 here. Let me erase this part and make it green. The 3 came from the iron. And of course, there is specified a 1 here. And you can see it's already matching up with the charge on the chloride anion. So you do want to make sure that those charges that are known are matching up, because if they don't match up, it means that is a case where crisscross did not work and you need to go back to your algebra. Excuse me. Okay, so this is iron with a charge of 3. So I'm going to use the Roman numeral system, 3. And then chlorine is kind of hiding back there. It's a monoatomic ion, which means I need to change the ending to IDE. So this is chloride. I know it's a lot of work. So this is why I did this one last and I did the other way first. Let's go on to our next example. So now we have a very similar compound, but it's not quite the same thing, right? So this is FeCl2. Again, it's still iron. It's still a transition metal. We can go ahead and name it, but we need to figure out what the charge on the iron actually is. So again, if I call the charge on this iron X, this time I have 2 chlorines. They each have a charge of -1. We have a neutral compound. So that means the charge on my iron is now 2, not 3. So this is iron 2 chloride. Again, remember that the Roman numeral does not tell you how many atoms, but it tells you the charge. I know I'm like a broken record. I keep saying it over and over and over again because I see this mistake over and over and over again. Okay, let's keep going with all of our transition metals here. How are we doing? Okay, so we're a little bit over on time. So what I will do is I will finish up these transition metal names, and then we can be done with this. All right, so ZR. So this is where you're going to have to use your periodic table and you're going to have to find where that is. It's actually zirconium. It is atomic number 40. Now, when you find, oops, I need to write zirconium. When you find that metal and you find that it's right smack in the middle of the periodic table, you need to go, transition metal, I'm going to have to specify the oxidation state. Okay, so that means we need to use our anion too, right? Okay, we don't know what the charge is on zirconium, but we do recognize this CO3, right? This is a polyatomic ion. This is carbonate. It's right here. And we know its charge. Its charge is -2, but I have 2 of them. So remember those parentheses. So I have 2 carbonates. They have a charge of -2. This is a neutral compound. So what must X equal? Again, you just do a little bit of algebra. X equals 4. So the charge on the zirconium is 4, which means I need to write 4 as a Roman numeral. And now I can name my carbonate. And that's it. I'm done. So this is a case where if you tried to reverse crisscross, it would not work, because you would have taken this 2 up to the charge of zirconium, and that is absolutely not correct. One thing that that can help you identify when it's not going to work is, of course, there's assumed to be a 1 here, and that would have gone back to the carbonate, but the charge on carbonate is not -1. The charge on carbonate is -2. So that is not matching up with the charge. So that is your high sign. Wait, stop, don't do reverse crisscross. It's not going to work. Okay, let's go on to our next one. So CO is cobalt. And cobalt is atomic number, where did it go? 27. Again, you can see it's right in the middle of all those transition metals. We're going to have to specify its charge. So cobalt, I don't know what its charge is. I'm going to call that X. I need to identify my anion. This is NO2 right here. This is nitrite. You can see it has a charge of -1, but I've got a parentheses. I have 3 of these. But we do have a neutral compound. Again, this math is pretty easy. X equals 3. This is one where reverse crisscross absolutely would have worked. Because again, there's a 1 here, and we do know that the charge on nitrite is -1. So that's totally fine. So let's specify this. The charge on the cobalt is 3. And then this is nitrite. Okay. All right. So we've got one more here. SN, this is actually 10. So it's atomic number 50. So it's a little bit farther over to the right, but it's still a transition metal. You cannot predict what the charge is going to be just based on where it is in the periodic table. So we are going to have to specify it. Now, this one is a little bit trickier because we have 3 of them. So instead of just calling 10X, it's going to be 3X. So our algebra is going to be a little bit more difficult, but again, I'll show you how to simplify this. Now we need to identify our anion, PO4. That's a polyatomic right here. It is phosphate. Its charge is -3, and I have 2 of them, so I've got 2 multipliers here. Plus 2 times -3. Again, this is 0. Now, you can solve for X, and you'll get X equals 2, and that's not a problem. But this is a case where reverse crisscross will really help us, because this 2 comes up to the charge on 10, just like this 3 came back to the charge on phosphate. So you can see that 3 is matching up with the charge on phosphate of -3, which means you can reverse crisscross. So this is 10. The charge is 2 phosphate. And that is the name of this compound. Okay, so I hope that these examples helped you with all of these different naming scenarios, because we've got the monoatomic ions, we've got the polyatomic ions, and we've got the transition metals. And we've got to bring them all together, especially in these examples here with the transition metals, and use all of those skills to figure out what the charges are. As always, please let me know what you find most helpful. If you would like to request a topic for a different live stream, you can leave a comment in this video. You can contact me on Facebook. You can shoot me an email. That's totally fine. We just want to make sure that we are doing live streams that are matching where you are in class and what you are going to find most helpful. And thank you so much for joining us today. Bye.